world's greatest natural wonders. The Grandeur Falls, a thundering series of 18 waterfalls straddling Brazil and Paraguay, which roared so loudly that it could be heard from over 30 kilometers away.
Fact 1. In 1966, Brazil and Paraguay signed the Treaty of Itaipu, establishing a joint authority to develop hydroelectric power on the Paraná River. The agreement defined equal ownership, construction financing, operational control, and long-term electricity allocation before engineering plans were finalized. This removed uncertainty around sovereignty and revenue that often disrupts binational infrastructure projects. Both governments committed to coordinated grid expansion, fixed pricing structures, and guaranteed purchase agreements so that electricity produced would have immediate demand. The treaty also created permanent joint administrative bodies responsible for engineering oversight, procurement approval, and financial coordination. These institutions prevented political turnover from altering project scope mid-construction and allowed engineers to lock specifications years in advance. Currency handling, debt servicing, and supplier contracts were coordinated across both national economies, stabilizing procurement timelines and ensuring uninterrupted material flow throughout the build. Fact 2. Engineers selected the site after analyzing decades of hydrological data from the Paraná River basin. The chosen location provided stable year-round discharge and a favorable elevation drop without requiring excessive dam height. Geological investigations confirmed a continuous basalt bedrock layer beneath sediment deposits capable of supporting extreme compressive loads. Extensive core drilling mapped fracture density, permeability, and load-bearing capacity across the entire footprint. These findings reduced uncertainty around settlement and uplift pressure and eliminated the need for deep anchoring systems. The basalt foundation allowed designers to optimize dam thickness, spillway placement, and powerhouse alignment with confidence that stresses would distribute uniformly under full reservoir conditions. This geological reliability shaped every structural decision that followed. Fact 3. River diversion was one of the most complex and dangerous stages of construction. Engineers designed 2 temporary channels to reroute the Paraná River around the site while preserving downstream flow. Cofferdams isolated the excavation zone and were reinforced to withstand fluctuating water pressure and debris impact. During peak diversion, more than 40,000 cubic meters of water per second flowed through the channels. Continuous monitoring crews tracked erosion, vibration, seepage, and structural movement around the clock. Emergency materials and equipment were staged nearby to respond to leaks within minutes. A cofferdam failure would have flooded the site, destroyed heavy machinery, and erased months of progress in hours, making diversion control one of the most failure-sensitive phases of the entire project. Fact 4. Once diversion was complete, foundation preparation began across the full footprint of the dam and powerhouse. Crews removed all sediment layers to expose competent bedrock and created a level surface for uniform load transfer. Engineers injected pressurized grout into fractures within the rock to reduce permeability and prevent seepage beneath the structure. Drainage galleries were installed to manage uplift pressure during reservoir filling and long-term operation. Instrumentation embedded within the foundation measured pore pressure and seepage flow continuously. These measures ensured hydraulic forces could not undermine the structure from below and directly increased resistance to sliding, overturning, and progressive deformation over decades of sustained loading. Fact 5. Concrete placement followed a modular block construction method rather than continuous pouring. Each block measured roughly 20 meters by 20 meters, allowing precise control of curing conditions and internal temperature. Cooling pipes embedded in the concrete circulated cold river water to regulate heat generated during hydration and prevent cracking from thermal expansion. Sensors tracked temperature gradients and stress development in real time. Over 12 million cubic meters of concrete were placed using tightly sequenced schedules that coordinated mixing plants, conveyor systems, and tower cranes. The block method allowed localized inspection and correction during construction while maintaining long-term structural continuity across the entire dam body. Fact 6. The dam operates as a gravity structure relying on mass rather than curvature or anchoring to resist hydraulic pressure. At full reservoir height, lateral forces exert tens of billions of newtons against the upstream face. The dam counters these forces by transferring weight directly into the basalt foundation below. Its geometry minimizes tensile stress and concentrates compression where concrete performs best. Internal galleries allow engineers to monitor movement and temperature changes throughout the structure. Even during extreme inflow events and rapid reservoir fluctuations, measured deformation remains within millimeter-scale limits, demonstrating the predictability and durability of mass-based structural resistance. Fact 7. The powerhouse contains 20 generating units each, rated at approximately 700 megawatts. Water enters through massive penstocks and drives Francis turbines engineered for high efficiency under variable head conditions. Blade geometry, rotational speed limits, and pressure tolerances were optimized to prevent cavitation and vibration across a wide operating range. Each turbine and generator assembly weighs hundreds of tons and required millimeter precision alignment during installation. Units were commissioned sequentially, allowing partial generation to begin while construction continued. This staged startup reduced commissioning risk, validated control systems early, and delivered usable power years before full completion. Fact 8. Spillway design accounted for extreme flood scenarios across the Paraná Basin. Engineers analyzed historical flood records and projected worst-case inflow events to determine discharge capacity requirements. The stepped chute system dissipates kinetic energy as water descends, reducing erosion and protecting downstream riverbanks and foundations. At maximum capacity, the spillway can release more than 60,000 cubic meters of water per second. Air entrainment systems prevent cavitation damage, while reinforced concrete surfaces resist abrasion during prolonged releases. During test discharges, vibration and pressure behavior confirmed stable energy dissipation across the entire spillway length. Fact 9. Power transmission required separate electrical systems due to differing national standards in Brazil and Paraguay. Two frequencies operate within the same facility, supported by independent transformers, switch yards, and digital control systems. Load balancing protocols coordinate output in real time based on demand fluctuations in each country. High-voltage transmission corridors were constructed in parallel with dam completion to move electricity hundreds of kilometers with minimal loss. Redundant protection systems isolate faults without interrupting generation. This configuration allows the plant to function as two synchronized power systems within one structure while maintaining grid stability on both sides of the border. Fact 10. Structural monitoring systems embedded throughout the dam track deformation, seepage, temperature, and internal stress continuously. Thousands of sensors transmit data to a central operations center where long-term performance models compare current behavior to baseline projections. Engineers developed failure scenarios to assess downstream impact under extreme conditions. Emergency drawdown procedures allow controlled reduction of reservoir level if abnormal behavior is detected. Inspection crews access internal galleries year-round to verify instrumentation and structural condition. Decades after commissioning, the dam continues to operate within original design tolerances, converting river momentum into electrical output at continental scale. Subscribe to Grandeur Decoded for deep reconstructions of humanity's largest engineered systems.